everybody, we are DAT Engineering and Design. This is our CE162 presentation. To give you guys a brief overview, we're going to introduce you guys to the team along with the description of the project. Then we'll dive into the calculation of the loads along with the design for the bending moment and shear forces. After that, we'll talk about the calculations of the deflection along with the development length. And along with that, we're going to talk about the design for the one-way slabs, columns, and footings. And at the very end, we'll have a conclusion to wrap things up. To introduce ourselves from right to left.
My name is Eric.
My name is Alan.
I'm Teresa.
I'm Adrian.
And I'm Dat.
So for our project, we'll be designing and analyzing a three-story retail center with reinforced concrete in Santa Clara. It will feature showrooms, computer rooms, storage, all open offices, and etc. And for our project, we had to follow these properties and dimensions shown on the plans, as well as follow these codes listed in the table. Some constraints include that the max girder depth to be 30 inches, but they respect all the dimensions provided in the plans, and we had to only design with one-way slabs and the loads considered. And for our plans, the drawing on the left is our floor 2, and the drawing on the right is for floor 3.
Alright, thank you, Alan. Now moving on, we're going to start with the calculation of our loads. Before we calculate our loads, first we need to find the minimum heights or thicknesses for our sections. As you can see, we use these two ACI tables for that, and also the equations below. Here is a summarized table of our dead loads for the slab, beam, and girder. And then on the right-hand side, for any components that were included in these, such as the floor, walls, and roof, we reference ASCE 7.
Alright, so after calculating the loads, we now calculate for the distributed dead load and the point dead load. For the distributed dead load, we use this equation up here. We take into account the weight of the beam, the weight of the slab, the superimposed dead load, and the weight of the wall. After that, we solve for the point dead load. We take into account the half span, the wall load, the waist slab, and the roof load. Right here we have our frame B uniform dead load. Our highest is on the roof, and the lowest is on the mid-span of the second floor, where there's a gap in the middle. Up next, we have frame 3 uniform dead load and point load. Our highest uniform dead load is on the third floor, and also on the second floor in the mid-span, due to the gap in the middle, and we have walls there. And then also for our point load, it's indicated with the blue arrows. The highest is on the roof, and the lowest is on the second floor mid-span.
And here is our distributed uniform live loads. You can see this on frame 3. You can see the values listed here as well. And we're going to be focusing on this specific value right here for our example calculation. We first need to find our factor live load using this equation right here, where we found our KL value was to be number 2 because the loads are applied on interior beams from the ASCE 7-16. We also found our unfactored live loads from the ASCE 7-16 table 4.3-1. And after finding the factor live load, we multiply that by the tributary width to find the distributed uniform live load of that section. Here we also have our point live load. They follow a similar calculation process where we find the factor live load, except this time to find the point live load, we need to multiply it by the tributary area at the intersection between the beams and the girder. See the value right here.
Thank you, Eric. For our roof live load, we obtained the original distributed load based on ASCE 7, and then we had to multiply it by the reduction factors that are applicable based on the tributary width or tributary area and the roof slope. And in the end, for beam 3 and girder 1, we were able to obtain these values shown in the table on the right.
Alright, thank you, Alan. For the last live load, we have our rain load. First, we have to figure out the drainage system. We went with the 4 drainage system shown on this side here. After that, we have to calculate the floor weight using this equation. With the floor weight, we use it to find our hydraulic depth, and our static depth is very different. With that being said, we can use that to solve for our load.
Alright, thank you. Now we can move on to our first design process, which is flexure. So for flexure design, we could choose to design either singly or double. For this section right here, first I decided to show a sample calculation of a single reinforced section. I believe this section is from frame B. As you can see, if the calculated row from our given moments from our SAT analysis, which I will show later, is between row min or row max, we design it as singly. And now here's an example of double. If our row calculated was greater than row max, we would design it as double, including conversion stone. Here is our moment diagram given from SAT on frame B, and we focus on the second floor, which we labeled as beams 7 through 9. Here is a summarized table of our values that we got for our beams. As you can see, we decided to choose a uniform bar size of 6. Each beam is singly reinforced, and on the right-hand side, you can see the section design capacity. Moving forward, now here's our moment diagram for frame 3. I focus on sections 4 through 6 on the 3rd floor. Here is another summarized table. For these sections, as you can see, in the negative moments in section 4 and 5, we had designed it as doubly reinforced. The rest are single. And for this, we also chose the uniform bar size of 10.
Thank you, Tristan, for the flexure design. We then move on to exterior design. First, we have to solve for 3 things, which include the critical shear, the nominal shear, and the concrete shear strength. To check if we have a valid concrete shear strength, we have to check for this condition here. After that, to check for our shear reinforcement, we have to make sure that this holds true, and if it does, continue on to the design. Up next, we have to figure out if our dimensions are correct. To do that, we make sure this condition here holds true, and if it does, continue on with the spacing. For the max spacing, this is smaller of the X max 1 and X max 2, and for the required spacing, we will use distributed length. After the spacing, we will then solve for the number of stirrups using these equations right here. It will be the distance x divided by the spacing. For the distance x, we will use PU minus the PVC over 2 divided by the factor load. Right here is our shear design. We should shear diagram for frame B, and here is our, and we're focusing on the 2nd floor only. Here is a shear detailing for frame B 2nd floor. We have a uniform bar number of 3, consistent throughout beam 7, 8, and 9, and it ends off at PVC over 2. Up next, we have a shear diagram for frame 3, and we focus on the 3rd floor. Here is a shear detailing for that. It's also simple to frame B with the same bar size of 3 for sections 4, 5, and 6.
Okay, after the shear design, we started to calculate the deflection. For the deflection, we calculated the deflection of the single beam as shown in the image to the right here. And for that, we initially had to find the combined bending moment that is unfactored, which includes the dead load and the live load, with the equation shown right here. After that, we also need to find the properties of the beam. The beam properties that we calculated for are listed with the equations shown right here. And these properties are all used to find the effective moment of inertia. And in our case, we use the second equation displayed right here as our effective moment of inertia because our combined moment was greater than 2/3 of a cracking moment. From that, we can calculate our instantaneous, our time-dependent, and long-term deflection, which is shown in these 3 boxes right here, along with the corresponding values at the bottom. These deflection values are compared to the maximum permissible deflection given the ACI code to see if we have a valid deflection or not.
Moving on, we have our development link. We were instructed to construct our development link according to the ACI Detailing Manual from 2004 with these parameters, with these extensions and cutoffs. With that in mind, we can move on to our continuous beam detailing, which follows the 2004 Detailing Manual. You can see the length at which they extend past their respective columns for our hook, tension, and compression sides. We apply the same principles as well to our simple beam detailing, which also consists of these bars with their respective extensions.
After the development lengths, we started to design for the one-way slab. And for the one-way slab, we had to look at what kind of support conditions our slab we were working with. And then, given the ACI code, we were working with a 1-end continuous slab. And from that, we can determine our minimum slab thickness, which was determined to be 7 inches right here. Also, from our minimum slab thickness, we can also find our design cover along with our minimum steel reinforcement ratio shown in these 2 boxes right here. Then we need to calculate for our main reinforcement. And to find our main reinforcement, we have to find our slab loading, our moments, steel reinforcement ratio, area steel, and the required spacing for it. In our case, our spacing, we had a uniform spacing of 8.5 inches, and this is because our calculated row values at every single section shown in this image right here was less than the row min value, so row min had to be taken as the governing row value. We have to check that spacing to the 2 ACI codes that govern for the maximum reinforcement spacing, and the least of these 2 codes have to be compared to get your maximum spacing. For us, we have a maximum spacing of 12 inches for the main reinforcement. Additionally, we have to find the temperature reinforcement, which involves finding the minimum area scale, required spacing, along with the maximum spacing. But this time, they have codes that are different, slightly different from the main reinforcement. In our case, we have a temperature reinforcement spacing of 8.5 inches, and there is temperature reinforcement. It's just hard to see in this detailing right here, but there is temperature reinforcement going in and out of the page. Then we need to check for the shear, and to check for the shear, we have to find where the maximum shear is, which is at the base of this support right here. And we use that maximum shear to find our critical shear at a critical distance D. And we compare that critical shear to the concrete shear strength to make sure that our concrete one-way slab can handle the shear forces.
Thank you, Dak. So onto column design, we had to figure out the unfactored loads and moments for each of the column sections for each floor based on the different loading combinations that we had. As you see, this is our diagram. And then our data is summarized in this table. And as you can see on the images on the bottom, those are the different load combinations that we applied to our frame. From left to right, it will be load combinations 1 through 3. And in the end, we were able to determine that for floors 1 and 2, the columns would have a dimension of 22 inches by 23 inches, and our longitudinal bar sizes will be number 9, while our high bar sizes were number 3, and our data scale is shown on the table on the right. And then for floor 3, since there's less loads on it in general, we were able to determine that the columns would be 20 by 20 inches, with our longitudinal bar sizes to be number 8, and our high bar sizes to be the same, along the area scale shown on the right. And to make sure that our column design is valid, we have to make sure the bar spacing was sufficient according to ACI standards, and they were, as you can see on both tables for floors 1 and 2 and 3. And this is an example of our column detailing as shown here. And for our column interaction diagram for floors 1 and 2, we noticed that 4 of the cases were in compression, while 2 of them were in tension. And then for floors 3, all of the cases were in tension. Now moving on to footings, since our given soil stress was 3,000, we were able to determine that the effective soil stress was 2,150 PSF, along with our point loads shown here, which are factored and unfactored. And our soil properties are displayed in the table on the right. Afterwards, we were able to calculate the footing area based on the unfactored point loads and the effective soil stress to be this value. And in the end, we chose our dimensions to be 20 foot by 20 foot. And then we also able to determine the depth of the footing as well, as shown in this value. To make sure our footings are valid, we have to do a 2-beer shear check. And so we have to calculate the critical section perimeter, and then calculate the shear for the 2A, and then calculate the assumed depth based on the shear and the ACI code for shear, and then make sure it's below our, I'll make sure it's less than our depth for our footing, which it is. And then we also had to do a similar check with one-way shear, with a similar process as well, finding shear and then the depth, and then checking to make sure that it is less than our chosen footing depth.
Alright, now moving on, we have to calculate our area still required for our footings. Now we're introduced, so we need to first find our row values. We took our row value to be equal to 0.0033, but first we need to calculate our actual row value, which we did by finding our ultimate moment and our U values listed over here. After calculating them, we found that it was 0.0026, which is below our minimum row, so we take our minimum row to be 0.0033. After plugging that into our area scale equation, we got our area scale to be 23.55 inches squared. And our result, we chose 18 number 10 bars at a spacing of 13.5 inches in both directions. Afterwards, we need to check our bearing stress, which is listed in the calculation listed in this table over here. By comparing the N1 load with the ultimate loading, we found that it is adequate and it's greater. We also compare N2 with our 2-way shear and find that it's also adequate, and as a result, we use minimum dowels. To find the amount of dowels that we have to use, we apply the equation to find the minimum dowel area, which is 0.005 times the area of the column, which gives us this value here, and we chose 4 number 9 parts. Now we need to find the length at which the dowels are extended to the column and the footing, by applying these equations over here, and we find that it extends into the footing 22 inches and extends into the column 34 inches. And you can see then in our detailing graphics over here, the 33 inches, and it extends down there to 22 inches.
Alright, that concludes our presentation. As you can see from our results, our project timeline was approximately 97 days, and that if you follow our recommendations closely, you should receive a structurally sound retail center. Data engineering design would like to acknowledge everyone, like to thank the team, Professor Solomon, our evaluators as well, and our peers for helping us reach a successful conclusion. Thank you very much.
It was a very good presentation with most of the things that we wanted to see it in the presentation. We have here Professor Bumi like to see some good engineers who good instructions. So just show this the best of you. So if you can.
Well, I do recruit, so, but hopefully I can find really good people to join our company. But that brings us to the first thing, the introduction. You did quite well, but could be better. You really have to enunciate everybody's name. It has to be absolutely very clear, very emphatic. So whoever's going to interview you will really know you, remember you. And after the general introduction, then when you pass the presentation on to the next person, you also mention that person's name. And that person also introduce himself or herself again and again and again and again. So that the reason why it's so important is that when you interview for a job, even if you don't get it, the interviewer will remember you. Sometimes, there might be only one position that's open. There's so many people apply for the job. But there might be other positions open in the future. If you make yourself memorable, you have a chance. And also, if you have shown certain potentials, people will remember you. They might reach out to you, or they might be, a source of reference for you. Someone you can contact, you can talk to, and you can ask to be a mentor in the future. Yeah, so that's a very important thing. Next thing is loading. I am glad to see you spend a lot of time with loading, and many people get to do something about figuring out the loading for the project. Who did the radio load? Can you share with us what you learned? How you go about getting all the information to determine the radio load?
So the first thing I did was figure out the drainage system. I can go back to the.
It's gonna be quite well, sorry.
So after I figured out the drainage system, I then have to figure out the flow rate for each drain outlet. And then with that, I could use that to solve for our hydraulic depth. And we need to use a table from the ACI. And with that table, I can figure out the hydraulic depth. And then the static depth was already given to us as 2, and which is plug that in into that equation right there, and we got our rain load.
How do you get the intensity I? Where you get it from?
We used the ASCE hazards tool, and we took the location at Santa Clara, the location of the building, and yeah, that's what that.
You know they still have tables that you can actually read off the eye, the intensity. Now you don't have to. You can it's quite amazing. Now who did the dead room?
We all.
Oh, you all did. Who would like to answer the question? How you get the dead rooms of each item?
We got that from a table ASCE 7, I believe it was table C 3.3.1. And that's where we got the superimposed depot.
In your presentation, in your drawings, do you have a section through the roof or the floor, typical section, that will show you every item that makes up your demo?
Would you be able to repeat that question? My apologies.
Basically, how you account for all of the elements for your roof and for your floor. You have a sketch that lists every item. For example, on the roof, you have the roofing material, you identify what it is, how thick it is, and then, whatever membranes and so on, and whether you have mortar or whatever on top of your concrete slab and so on.
So Alan would like.
Yeah, we do have our models, but unfortunately they're not in our presentation, but they are in our design report. Yes.
In the drawing you have that. Okay. All right, we can jump to flexure. Put it flexure, okay? Now, you ran through the process of doing that. You even have the example beam analysis. Can you just briefly describe the process of designing a beam?
Like designing a beam.
A beam.
Yeah, so since we're given the external moment, we know that we need to find the dimensions of the concrete. So first, we got our row. As you can see there, we use that row equation from, we used our factored moment there and then solved our calculated row. From there, I looked to see if it was row, when we calculated row min and row max and compared to see if it had to be single or double. And then from there, we calculated an AS, and from AS calculated, we looked at the bar size we chose between 6 through 10, and we chose the closest value. And from there, we chose our bar size and bar numbers, and then calculated the minimum width of the concrete using the B-min equation. From there, we were able to decide how many bars were in row, and then for this section specifically, since there were 8 bars, since it's 8 bars, we know we have to design as 2 rows. And then from there, using our AS chosen, we put it into the section design capacity to check if our section design capacity was greater than our factor moment.
The dimensions given to you in the project for your beam size, is that already given?
We came up with these dimensions earlier, right here, using these. We chose some dimensions, but for these, so for our B line, for example, we chose that, but for lengths and other such, they were given to us.
So you chose the dimensions in the beam. Is not given. They're not given. I see. And did you do the deflection analysis?
No.
No. Okay. Now, what's the significance of the maximum reinforcement, the Romex? Can you?
Row max is 2.
Why you have to limit your reinforcement not to exceed Romex?
I believe it's because if you add too much reinforcement, the force will go into the concrete. I believe that's it. And then if that occurs, then there's too much reinforcement.
All right, thank you. Now, one-way slab. Who did the one-way slab? Now, how do you get all the forces to design your concrete slab?
Okay, so to get the forces, we had to look at basically the dead loads and the live loads that are put onto there, and then we multiply it by 1.2 for the dead and 1.6 for the live to get the ultimate loading on the slab.
Then how do you find the moments? You have to do the structural analysis to find the coefficient you show there.
So to calculate for the moments, we use this diagram right here, which shows you the different moments, the different positive and negative moments at the spans of each beam when we're designing the slabs. And so the moment is different at different sections of the slab, depending if it's a positive moment, negative moment, or if it's against the support. And because it's different at every location, it's going to have different coefficients in terms of how to calculate, in terms of what the moment is. But in this case, when we calculated all of our moments, we then found our RU value, and then after that we used it to find our rho value. And that rho value for all sections ended up being less than our rho min value. So then we had to end up taking all this, every section right here as a rho min value, as a rho value, as the rho min was the governing rho value.
Okay. What I was asking about is how we get the coefficients, where do we come from the analysis or
So for the coefficient,
the moment coefficient?
there is somewhere in the code book.
Well, that's a partial answer, that's okay, it comes from the book.
So, yeah,
But
it
the
comes from the
book,
book, and it shows all the positive and negative,
But the book,
yeah.
is referring to probably a governing code.
Right.
That's a partial. I have another question, regarding shear. For concrete slabs, if you have, suppose you are required, based on the thickness you chose, you're required to reinforce for shear, what would you do?
Are you asking for the concrete slab or are you asking for the shear design?
No, I mean, this is a hypothetical question. I see that whatever you put in works here, but suppose that the thickness of the slab that you input in your design, your analysis here, show that is not adequate, you need to reinforce it. In that case, what would you do? You have to reinforce it for shear. Would you?
If I have to reinforce the slab,
In your case here, does the design shear force exceed the shear capacity of your slab?
oh, see. So you're asking if if it's,
Are you asking if our depth was like too big or not? It's not adequate?
I'm asking based on your design here, do you have to reinforce for shear?
oh, yeah, we have to reinforce, we have
This is
to,
for the slab.
For the
It's not
slab?
slab.
Oh,
Yeah.
for the slabs, oh, so for the slabs, we don't need shear reinforcing it, because when we looked at our shear at a critical distance D, which I think a better visual to look at it is something like this right here. When we look at it at a critical distance D, and we compare that to the concrete shear strength, in our case, when we look at it, our concrete shear strength was greater than our shear at a critical distance D. So,
I see.
so that's why, we don't have any sort of, shear reinforcement for the one-way slab.
But suppose it's not as ideal as this case. Suppose the number shows that it is required to reinforce for shear. What would you do? I mean, you're free to do whatever, but what would you choose to do?
So the value of the shear, the value of the shear you calculated at D
Yeah.
was larger than the capacity of the concrete in shear. What to do?